Hello everyone, I'm Lowell Jhon Dolueras. The topic that I will discuss to you is about elastic properties of materials. So what is elastic or elasticity? When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find out in this video. Let's take an example of a helical spring, which a force of compression or tension is applied. The helical spring gets deformed. That is, the changes shape and size. This force is referred to as the deforming force, and the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge ball and rubber bands. When compressed or stretched, they get deformed, but they soon return to their shapes. This sense reversing deformity the object goes through when the force applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to spring, it simply will not be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. This type of deformation where the object is unable to attain, or if it only partially attains its original shape once the deforming force is removed, is called plastic deformation. Suppose we have a rubber string and string made of steel, both of a very tiny thicknesses. Both are identically to each other in terms of size and shape. If we stretch them from the both ends with equal and opposite forces, then which one will stretch the farthest? Assuming the deformation is elastic in both the cases. Quite obviously, the rubber string will stretch the farthest. So steel string would barely stretch, but it is important to note that it would needed stretch no matter how little. It doesn't stretch or fast as a rubber string because steel applies more resistance to the deforming force than the rubber does. Moreover, as soon as the force is removed, the steel string regains its original shape and size quicker than the rubber string. It will not allow a deforming force to change its dimension as easily. So which would say is a more elastic, steel or rubber? You would think that the obvious choice has to be rubber, but fortunately is incorrect. There is a general misconception that a lot of us have about elasticity. We think the more the objects get stretched or compressed, the more elastic it is. But elasticity is not the same as a flexibility. In the language of physics, the term elastic has a different meaning. In physics, we say a body is a more elastic if it resists more to the deforming force and reverses back quicker to its original shape after the force is removed. And since steel resists more and reverses back to its original shape quicker, it's more elastic than rubber. We can mathematically define elasticity as the ratio of stress to strain. So there are two formulas are we gonna use in elastic properties. These are Hooke's law and Young modulus. So what is Hooke's law? Hooke's law states that the strain of the material is proportional to the applied stress within the elastic limit of the material. When the elastic materials are stretched, the atoms and molecules deform until stress is removed, they return to their initial state. Mathematical, Hooke's law is commonly expressed as F equals negative kx. In the equation, F equals is the force, x is the extension length, k is the constant of proportionality. And what is Young modulus? Young modulus or plastic modulus or tensile modulus is the measurement of mechanical properties of linear elastic solids like rods, wires, and etc. There are some other numbers exist which provide as a measure of elastic properties of material. Some of these are bulk, modulus, and shear modulus, and etc. But the value of Young modulus is mostly used. This is due to the reason that it gives information about the tensile elasticity of material. The formula for Young modulus formula is as follows according to the definition. E equals sigma all over epsilon. We can also write Young's modulus formula by using other quantities. E equals F times LO all over A times change of L. Notation used in the Young modulus formula where E equals Young modulus in and sigma the uniaxial stress, epsilon the strain or proportional deformation, F equals the force exerted by the object under tension, A equal it is the actual cross-sectional area, change of L it is the damage change in the length, L of O it is the actual length. And these are the examples of Hooke's law. Our example problem for today, we have a force of 50 Newton is applied to a spring with a spring constant of 400 Newton per meter. How far back is the spring compressed? And so on the right hand side, you see that listed the Hooke's law equation, F equals Kx. F represents our force, K represents our spring constant, and X represents the distance that the spring is either compressed or stretched. And then underneath that I have a picture representing this problem. We have a spring that's being pushed back 50 newtons and we want to know how far the spring compressed. And so as we begin, we need to list our knowns and unknowns. So we know that we have a force of 50 newtons. And we also know we have a spring constant of 400 newtons per meter. That's our K value. And then lastly, we want to know how far is this spring compressed. So that's our X value. So from this point, we are just gonna plug in our values into our equation. We have 50 Newton of force. That's gonna equal 400 Newtons per meter times our distance. To get X all by itself, we will divide by 400 on both sides. And we end up with an answer of 0.125 meters. So that's how far back it was compressed. And here is the example number 2. This just says that we have force 2.5 newtons. Attached to a spring, we get a change in the length of 16 centimeters. And we want to know what is the spring constant K at that spring. So we're just calculating the spring constant. We get out the Hooke's law equation. We solve that for K. And that is the force divided by the change in the length of force. We said 2.5 newtons. The change in length is 0.16 meters. And that means that the spring constant for the spring is 15.6 Newton per meter. That means we would have to apply 15.6 Newtons force to change the length of the spring by 1 meter. And these are the example of Young modulus. Our first example for Young modulus. Find out Young's modulus value of a material whose elastic stress and strains are 4 Newton all over meter per square and 0.30 respectively. So the solution is stress sigma equals 4 Newton meter raised to negative 2 and strain is epsilon equals 0.30. So Young's modulus formula is E equals sigma all over epsilon. Substituting values, we get E equals 4 all over 0.30 and E equals 13.30 Newton meter and negative 2. Thus Young's modulus is 13.33 Newton meter raised to negative 2. Here comes another example. Young's modulus for brass is 8.96 times 10 raised to 11 Pascal. A 120 Newton weight is attached to an 8-meter length of brass wire. Find the increase in length. The diameter is 1.5 millimeter. First, find the area of wire. So A equals pi d square all over 4 is equal to pi times 0.0015 meter square all over 4. So A equals 1.77 times 10 raised to negative 6 meter per meter square. So the formula that we're gonna use is y equals F times L all over A times change of L, or change of L equals to FL all over AY. So y equals to 8.96 times 10 raised to 11 Pascal. L equals 8 meter. F equals 120 Newton. A equals 1.77 times 10 raised to 6 meter square. So we gonna solve for change of L. So the formula that we gonna use is change of L equals F times L all over A times Y. So change of L equals to 120 Newton times 8 meter all over 1.77 times 10 raised to negative 6 meter square times to 8.96 times 10 raised to 11 Pascal. So the answer is change of L equals to 0.005 millimeter.